Hello students, we are going to see about Bayesian classification. Bayesian classification is based on Bayes' theorem. It can be also referred to as statistical classifier. Bayesian classifiers can predict the class membership probabilities, that is, the probability a given tuple belongs to a particular class. Now we will see the Bayes' theorem. Bayes' theorem was named after Thomas Bayes. There are two types of probabilities. They are posterior probability represented as P of C given X and prior probability represented as P of C, where X denotes data tuple and C denotes hypothesis. Bayes' theorem finds the probability of an event occurring and the probability of another event that has already occurred. Bayes' theorem stated mathematically as the following equation. Probability of C given X is equal to probability of X given C into probability of C divided by probability of X. It can also be written as probability of X1 given C into probability of X2 given C so far up to probability of Xn given C into probability of C. Here, probability of C given X is the posterior probability of the class which is the target, given predictor which is the attribute. Probability of C is the prior probability of class. Probability of X given C is the likelihood which is the probability of predictor given class. Probability of X is the prior probability of predictor. In 0-OR model, there is no predictor. In 1-OR model, we will find the single best predictor. In naive Bayes includes all predictors using Bayesian rule and the independence assumption between predictors. Bayesian belief network. Bayesian belief networks specify joint conditional probability distribution. They are known as belief networks, Bayesian networks, or probabilistic networks. It defines class conditional independencies between subsets of variables. It provides a graphical model of the relationship on which learning can be performed. A trained Bayesian network can be used for classification. Now we will see the major components of a Bayesian belief network. They are a directed acyclic graph, a set of conditional probability tables. Now, what is a directed acyclic graph? Each node represents a random variable in a graph. Variables may be discrete or continuous valued. It may correspond to the actual attribute given in the data. Now we will see the directed acyclic graph representation. The diagram shows a directed acyclic graph for 6 Boolean variables. The arc in the diagram represents causal knowledge. For example, lung cancer is influenced by a person's family history of lung cancer as well as whether or not the person is a smoker. It is worth noting that the variable positive X-ray is independent of whether the patient has a family history or that the patient is a smoker, given that we know the patient has lung cancer. Now we will see conditional probability table. The table shows the conditional probability for the values of the variable lung cancer denoted as LC, showing each possible combination of the values of its parent nodes, family history represented as FH and smoker represented as S. Now we will see in detail about naive Bayes classification. Naive Bayes is a simple and commonly used machine learning classifier. It is a probabilistic classifier that makes classification using posterior decision rule in a Bayesian setting. It can be denoted using a very simple Bayesian network. Naive Bayesian classifier is popular for text classification and for problems such as spam detection. We'll see about the model. The main goal of the probabilistic classifier is to determine the probability of the features occurring in each class and to return the most likely class given the feature x0 through xn and classes c0 through ck. Therefore, for each class we want to calculate probability of ci given x0 through xn. To do this, we use the Bayesian rule which is given by probability of A given B is equal to probability of B given A into probability of A divided by probability of B. In the context of classification, you can replace A with a class Ci and B with our set of features x0 through xn. Since probability of B serves as normalization and we are usually unable to calculate probability of x0 through xn, we can simply ignore that term and instead just state that probability of Ci given x0 through xn is proportional to probability of x0 through xn given Ci into probability of Ci. Probability of Ci is simple to calculate. It is just the proportion of the data set that falls in the class I. Probability of x0 through xn given Ci is more difficult to compute. In order to simplify its computation, we make the assumption that x0 through xn are conditionally independent given Ci, which allows us to say that probability of x0 through xn given Ci is equal to probability of x0 given Ci into probability of x1 given Ci into so far up to probability of xn given Ci. This assumption is most likely not true, hence the name naive-Bayes classifier. But the classifier nonetheless performs well in most situations. Therefore, our final representation of class probability is probability of Ci given x0 through xn is proportional to probability of x0 through xn given Ci into probability of Ci, which is proportional to probability of Ci product over j equal to 1 to n probability of xj given Ci. Calculating the individual probability of xj given Ci terms will depend on what distribution the features follow. For a text classification, features may be word count. It may follow a multinomial distribution. In other cases, features may be continuous. They may have to follow a Gaussian distribution. Note that there is a very little explicit training for naive-Bayes compared to other classification methods. The only issue is to find the parameters for the feature's individual probability distribution quickly and deterministically before prediction. It means that naive-Bayes classifiers can perform well with high dimensional data points and for a large number of data points. Now we'll see classification using naive-Bayes method. With a way to estimate the probability of a given data point falling in a specific class, we can use this to produce classification. Naive-Bayes handles this in a very simple manner. Simply pick the Ci which has the largest probability given the data points feature. Given this, now we have y is equal to argmax over Ci of probability of Ci product over j equal to 1 to n probability of xj given Ci. This is called the maximum posterior decision rule. This is because, referring back to our formulation of Bayesian rule, we use only the terms probability of B given A and probability of A, which are the likelihood and prior terms respectively. If we are using probability of B given A, the likelihood, we will be using a maximum likelihood decision rule. To start with, let us consider a data set. Consider a fictional data set that describes the weather condition for playing a game of golf. Given the weather conditions, each tuple classifies the conditions as fit, meaning yes, or unfit, meaning no, for playing golf. Here is a tabular representation of the dataset. We divide the dataset into two parts, namely feature matrix and response vector. Feature matrix contains the rows of the dataset in which each row consists of the value of dependent features. In the above dataset, features are outlook, temperature, humidity, and windy. The response vector contains the value of the class variable, that is prediction or output, for each row of the feature matrix. In the above dataset, the class variable is play golf. Now we'll see the assumptions. We assume that each feature makes an independent and equal importance to the outcome. With relation to our example dataset, we assume that no pair of features are dependent. For example, the temperature being hot has nothing to do with the humidity, or the outlook being rainy has no effect on the winds. Hence, the features are assumed to be independent. Secondly, each feature has given the same importance. For example, knowing only the temperature and humidity alone cannot predict the outcome accurately. None of the attributes is irrelevant and assumed to be contributing equally to the outcome. The assumptions made by naive Bayes are generally not correct in real-world situations. In fact, the independence assumption is never correct, but it works well in practice often. We put the naive assumption to the Bayes theorem, which is independence among the features. Here, the evidence is split into the independent parts. If any two events A and B are independent, then probability of A, B is equal to probability of A into probability of B. Now we have to create a classifier model. For that, the probability of the given set of inputs for all possible values of the class variable should be found, and the output with maximum probability is selected. Now let us apply the above formula manually on the weather dataset. For this, we need to do some pre-computations on our dataset. We need to find probability of xi given yj for each xi in x and yj in y. There are 14 rows, out of which 9 have target yes and 5 have target no. Now for all the attributes, the probabilities are calculated as given in the tables. For example, probability of playing golf given that the temperature is cool, that is, probability of temperature equal to cool given play golf equal to yes is equal to 3 by 9. Also, we need to find class probabilities, probability of y, which has been calculated in the table. For example, probability of play golf equal to yes is equal to 9 by 14. So now we are done with our pre-computations and the classifier is ready. In this example, the posterior probability is calculated by first constructing a frequency table for each attribute against the target. Then transforming the frequency tables to likelihood tables are finally done using the naive Bayes equation to calculate the posterior probability for each class. The class with the highest posterior probability is the outcome of prediction. Now, considering our example, let us calculate probability of x given c. In our case, probability of sunny given s is equal to 3 by 9, which is equal to 0.33. Next, we calculate probability of x. In our case, probability of sunny, which is equal to 5 by 14, which is equal to 0.36. Next, we calculate probability of c, that is equal to probability of s equal to 9 by 14, which is equal to 0.64. Now, we'll calculate the posterior probability. Probability of c given x, which is equal to probability of s given sunny, that is equal to 0.33 into 0.64 divided by 0.36. Finally, we get 0.60 as the posterior probability. The likelihood tables for all 4 predictors is given in the picture. The method we have discussed is applicable for discrete data too. In the case of continuous data, we need to make some assumptions regarding the distribution of values for each feature. The different naive Bayes classifiers differ mainly by the assumption they make regarding the distribution of probability of xi given y. One such classifier is Gaussian naive Bayes classifier. In Gaussian naive Bayes classifier, continuous values associated with each feature are distributed according to a Gaussian distribution. It is also called normal distribution. When plotted, it gives a bell-shaped curve which is symmetric about the mean of the feature values as shown in the picture. Other popular naive Bayes classifiers are Multinomial Navier Bayes. Feature vectors represent the frequencies with which certain events are generated by a multinomial distribution. This type of model is typically used for document classification. The next one is Bernoulli-Navier Bayes. In this multivariate Bernoulli event model, features are independent Booleans describing inputs. Like the multinomial model, it is popular for document classification tasks where binary term occurrence feature, that is, a word occurs in a document or not, are used rather than term frequencies, which is nothing but the frequency of a word in the document. Now we'll see the advantages and disadvantages of Navier Bayes. On the advantages side, it is easy and fast to predict class of test dataset. It performs well in multi-class prediction. The next advantage is Navier Bayes classifiers performs better compared to other models like logistic regression and needs less training data in case of assumptions of independence. The next advantage is compared to numerical variables, it performs well in categorical input variables. Normal distribution is assumed for numerical variables. Now we'll see the disadvantages. If categorical variables has a category which does not appear in the training data set, then model will assign a zero probability and will be unable to make a prediction. This is known as zero frequency. To solve this, we can use the smoothing technique called Laplace estimation. Navier Bayes is a bad estimator is one of the disadvantages. Another limitation of Navier Bayes is the assumption of independent predictors. In real life, it is impossible to get a set of predictors which are completely independent. Finally, to conclude, Bayesian classifiers are statistical classifiers. They can predict class membership probabilities such as the probability that a given tuple belongs to a particular class. Bayesian classification is based on Bayes' theorem. Bayesian classifiers have high accuracy and speed when applied to large databases. Naive Bayesian classifiers assume the effect of an attribute value on a given class is independent of the values of other attributes. This assumption is known as class conditional independence. Naive classifier is very easy and fast to predict the class of test dataset. It performs well in multi-class prediction. Limitation of Naive Bayes is the assumption of independent predictors. In real life, it is impossible to get a set of predictors which are completely independent. Thank you.